Okay, everyone, the last thing that I want to do to finish out your winter break homework is to do a few graphs for you all so you guys get an idea how your graph's going to look like. I'm going to do number 1 with you all, and I'm going to do number 3 with you all, and I want you to do number 2 on your own. So before I do these graphs, let me remind you how the path of motion looks like for a cannonball. When we fire it, the cannonball goes up, stops, and comes back down. And remember, for this ranking task, we're going to consider anything moving up to be moving in the positive direction, and anything that's moving down, we're going to consider it's moving in the negative direction. Okay, so keep that in mind as we're working out number 1. Number 1 says, from the ranking task for situation A, please provide a position time graph, a velocity time graph, an acceleration time graph for the vertical component of the cannonball while it is traveling upward. So in other words, for number 1, we're solely focusing on what's happening in the y direction. So if I have a cannonball, okay, and I launch it here in A, it's obviously going to look something like this. It's going to go up, stops, and comes back down. Okay, and this is the point where it just comes to a stop there for a brief moment of time before it comes back down. So remember, as the cannonball goes up, there's only one thing acting on it, and that's gravity, because we are ignoring air resistance. So if gravity is acting on it, and that means that the cannonball must be slowing down. In other words, it's slowing down while moving in the positive direction. So how does that look like on a position time graph? Well, that's easy. Y'all know how that looks like. If you're going up, that means your position time graph must be going uphill, and it must be coming flatter with time. So it flattens out, because becoming flatter with time means it's slowing down. So it's slowing down in the positive direction. So that's your position time graph. What about your velocity time graph? Well, for a velocity time graph, we have to be drawing our graph on the positive side. In this case, we're approaching 0 with time, because approaching 0 means that we're slowing down. Oh, and remember, if gravity is the only thing acting on this object, that means its acceleration must be negative 9.8 meters per second squared. So in other words, the slope of this graph here, the slope of this line is equal to 9.8. So, and you clearly see that that's a negative slope, because gravity is acting in the negative direction, and the slope is equal to 9.8. So, which means that our acceleration, we have to draw it at a constant negative 9.8. What I'm going to do here, I'm going to count by 5. So this is 0, 5, 10. So I'm going to draw my graph here close to negative 10. So right there, just close to negative 10. And I'm going to label that negative 9.8. And to demonstrate that the point there is negative 9.8, which is close to negative 10. Okay, so that's number 1. That's how your graphs look like for the vertical component. But what about number 3? Number 3 says provide a position time graph, a velocity time graph, and acceleration time graph for the horizontal component of the cannonball. Note, moving to the right is moving in the positive direction. So how does that look like? So remember when we see it, the cannonball is fired, it goes up, stops, comes back down. Okay, so that's how its overall path of motion looks like. But keep in mind that what we're considering here, we are only considering what's happening in the x direction. So again, we're only considering the x direction. So that's why we're drawing an arrow here showing I'm solely looking at the velocity in the x direction. Well, remember guys, there's no forces acting in the x direction because gravity only acts in the y direction. So if our cannonball is fired with an x velocity of 20 meters per second, then what do we know about the velocity from here to the very end, to this point here? Well, we know that the velocity must be constant because there's no forces acting there. So whenever we're considering the horizontal component, our position time graph must show a constant positive velocity. So the position time graph has to look something like this. And again, it's understood here that this slope here is equal to positive 20 meters per second. Okay. Because remember, the slope of a position time graph tells us our velocity, and our velocity is just 20 meters per second, okay, in the x direction, and it remains constant. So how would our velocity time graph will look like? So remember, we're counting by 5, so 5, 10, 15, 20. That means our velocity time graph is going to be somewhere right here, okay, at a constant velocity in 5, 10, 15, 20. And again, it's understood here that this point here, this velocity point, again, that's at 20. Now, what about our acceleration? Well, that's easy, guys, because if we're moving at a constant velocity, that means we must have 0 acceleration. So our acceleration time graph looks something like this. So the acceleration is just at 0. Okay, so that's your graph for number 3. Those are your graphs that are representing the horizontal component of the velocity as the cannonball is being fired. There you go.